Here's my next circuit. What do I want you to do? Look at it. The numbers may be hard to come by here, but what do I want you to do? Think your way through it. Is it charging? Is it discharging? Am I adding resistance? Then it should be discharging. If I'm making things more in parallel, it should increase the voltage. Okay? Give it a shot. Okay, let's look at the circuit. So what we're doing here is that we're going to throw the switch at t equal to 0, close. So let's look at this guy. So the first thing that we want to look at here is that when I look at this, if this thing is open, I see the 4-volt source here. And so I don't know the direction of the current, but I would probably guess that the current is coming up this way into that node. So if it's coming into that node, that is definitely coming into this node. So I could see two sources now are feeding that capacitor, charging it up. So I see two sources. But if now that switch is thrown, what ends up happening is that I kill off the 4-volt source of the 2K. So now it only sees one source, that guy, because this guy's gone. So it should be feeding that capacitor less. So I would claim here that, so if I was to interpret before I go there, I would say that at t equal to 0 minus, two sources add to VC 0 minus. Right? At 0 plus, there is only one source. So that implies that I would expect a discharge. Right? That it's discharged. So intuitively, that's what I would expect here. Now note, the capacitor value only makes sense when I do what? When I go to calculate the tau value. Or if I got to calculate something that's doing that. But this guy is 100 microfarad. Now note, in my notes here, I wrote it differently. I have a curved capacitor. Now, I stopped doing the curved capacitor because people says, oh, that must be plus, that must be minus. And the answer is no. Okay? So I'm starting to draw them straight so that people don't do that. So there I go, right? I got a 4-step process. What do I got to do? Go calculate VC 0 minus. Switch is thrown, make it into a Thevenin RC circuit. Once you do that, put it into solution form. Once I got into solution form, go back to the original circuit and solve the problem. What am I solving for? The current IX of that 2K resistor. Yes?
Can you say how you know it's discharging?
So at 0 minus, this is open, so I got the 4-volt feeding and the 4 milliamp source feeding that cap.
Okay.
But when I throw that switch, that 4-volt goes away. Because I've shorted it out. Right? Because imagine this here. I can also draw this like this. Right? So if I look at this guy, right? I have this guy. Or I can draw this like this. So you see, it's essentially pinches off. Right? There's the famous or infamous pinch. Apparently I used to say that and people said, like, what do you mean pinch? What do you mean? I mean back. I just pinch that thing, I pinch that thing right off. Okay? Hopefully that language. Lingo may be saying, like, what the hell is that, right? Because he's using English as a second language, and I'm impressed. So, let's do do that step process, right? You got to get into a rhythm here. VC 0 minus, throw switch, convert to Thevenin. From Thevenin, get those parameters. From those parameters, write the solution form. From the solution form, go back and use simple circuits to calculate for IX. Here we go. Damn, we're not going to finish here. So the step one here, we want to determine VC of 0 minus. So here I go. So the circuit is open. So the first thing that I want to do here is, what am I going to do? I'm going to simplify this thing. These and this should be one resistor. Right? So I got 6 and 12, so that should be a 4K resistor. So then I'm going to come over here, and I'm going to draw this as a 4K resistor. And then I'm going to get a 2K. And then I'm going to get another 2K. Then I have my open. Right? So this is what my circuit looks like. Okay, so it is true that we got to go after this guy right here. But the way we get that is we got to get what? I'm going to assume that this is positive and that's negative for VC 0 minus. Okay? So, how would you solve for that VC of 0 minus? Simple circuits, mesh, node, Thevenin. Hell yeah. Just look at that circuit. Follow the current. Look at the current. I know the current right away. So I know that this guy is 4, and that's a 2K. So 4 milli 2K, that gives me what? 8 volts. Okay? So I got that voltage, I got that voltage, but wait a minute. If I know that this is 4 milliamps right here, I could use the current divider rule across these guys right here. Right? The currents have to split like that. There's a lot of ways that you can do this thing here, but you can see that I could simplify this guy a little bit. So, how am I going to get this guy? So, think about that. Why did I say current divider rule? I can't use current divider rule because I didn't isolate it that way. But just look at the circuit though. Isn't that a 4K? Isn't this branch a 4K? So what's it going to do with that? Got to split it 2 milliamps each way. So when I look at this, that means that this guy's going 2 milliamps. This guy is going 2 milliamps. So here I go. So if I look at this guy here, you can see that this guy now must be what? Plus, minus right there. So what am I going to do? I'm going to apply the KVL loop here. So let's do that now. If that's my sign convention, here I go. So look what I do. I'm going to start right here. I'm going to get minus VC of 0 plus 8 plus 4 that I'm coming around. And now I'm getting a plus here. So it's got to be plus what? 2 times 2 gives me another 4. Must be 0. I think that looks right to me. So this tells me here that V0 has to be 1216. Right? Am I right here? I better get that answer. Good. I got that answer. So there's my voltage right there. I got my VC of 0 here. Okay? Now what happens? Switch is thrown. Okay? Step 2 now. So now I'm at the switch is thrown, and now I have an RC Thevenin circuit that I got to deal with. And that RC Thevenin circuit implies what? VOC, RTH, 1 over tau. Okay? Let's do that. Let's draw it out now. So now, here's my circuit now. So I'm going to keep my circuit the way I had it before. I have a 4K, 2, here's my cap, and then I have my current source right here. Right? So I got a 2K, and then I'm looking for the voltage of this guy, which I defined here to be VC of T right here. And this is 4 milliamps. Right? Let's make sure. So the switch is thrown, that kills off. So this is my circuit now. So when I look at this circuit, what am I going to do? I'm going to remove the load, and I'm going to determine VOC. There I go. So I want to now determine VOC. So there I go. So I get a 4K, 2K, current source, and then I have my open right here. Where I'm making this plus minus. So this is a nice circuit, you gotta admit, right? Because this is again very nice. Because look, there's only one branch, right? That's 4. We already saw that over here. I got a 4K here. I got 2, which is a 4K. So what does that mean? That means here I'm getting 2 milliamps. Here I'm getting 2 milliamps. So if I choose my ground, you can see that this guy's plus minus. So I'm going to go minus, plus. This tells me here that VOC must be the same as the voltage across what? The 2K. So I get minus, plus, equals to 0. That means this. So then it should be 2 times 2, 4 volts for VOC. Okay. So now I'm going to go determine RTH. No dependent sources here, so what am I going to do? I'm going to open that, and then I'm going to look for the Thevenin resistance there. So I got an open here. So I got a 2K, 4K. And so here's my 2K, 4K. So when I look at this here, now note this whole branch doesn't exist, but I'm just doing it to make it easier for you. This guy must be RTH. Damn, let me just calculate. Oh, hey, I got time. All right, we can finish the circuit. So what we'll find here is that let's follow the current, right? Follow the current. The current comes here, and then what does it do? It splits. So as it splits here, you can see that 2 is parallel to the 2 and 4. Right? So I'm seeing here that RTH has to be 2 parallel to the 2 plus 4. Okay? So it's got to be 2 times 6, 2 plus 6. That's 12 over 8, 4/3. No. 3 over 2, 1.5, thank you. RTA.
You can still use that whole thing where it's 1/3, so it's 1/4.
Yeah. Just for some reason I wrote it this way. And then the last thing I got to determine here is 1 over tau. So if I look at 1 over tau, it's got to be R Thevenin times C. So R Thevenin is 1.5 times 10 to the 3. Now, what is this guy? It's 100 microseconds. So your job here, if this is in microseconds, then what I probably do here is that I play with the powers of 10 here. So that's 10 to the 2 times 10 to the negative 6. Right? So I go 10 to the 2 times 10 to the negative 6. And you can see here that this is 5 and this is negative 6. So I should get 10 to the negative 1. 10 to the negative 1 means that I bring this over to 0.15. So I should get 1 over 0.15. You're probably not going to do that. You're probably going to punch it into your calculator. And when you do this, you get 20/3 in the end. Okay, wow. We almost did that. That was probably pretty fast. Your hair is kind of blowing back. I will see you on Friday last week, or otherwise Monday. Obviously, the due date for the homework is it's not correct on the website.
Well, actually, I said that on one hand, the powerful network is connected with other students. But then also, distractions and not a replacement for I got one little This took me all the time, we raced a lot. All right, we'll see.
Hey, let's get started here.
That's something I made.
Hey, so this is the problem that we were doing last time. Okay? So as you probably may realize, I stepped it up here. Right? This material is definitely more challenging, at least from past experience. Especially in the beginning, but then it settles down afterwards, after you figure out how to do this stuff. So, what we were doing here is that we were looking at this example 8.2, and this is what the original circuit looks like. And what we were wanting to do here is that we wanted to calculate the current IX. How do I calculate the current IX? By calculating the voltage across the capacitor, and then from the capacitor voltage, I then look at the circuit when the switch is thrown, and then I solve that problem. So here we go. What we said here is I asked you, without any calculations, to try to build intuition here, figure out if you think the capacitor is going to charge up or discharge. And what we said here is that we said that the capacitor would discharge. When I have this thing as an open, I have this current and then this current from the 4 volt that's feeding that capacitor, and we're expecting that that increases the voltage. When the switch is thrown, it shorts off the 4 volt source. So the only thing feeding the cap then is that 4 milliamps. Therefore, we think that it's going to discharge. So now we go into that process. Step 1, we determine the initial velocity of the cap. So using simple circuits here, we saw that there's only one current in the loop, right? Because that guy and that guy's in series. So as I come through here, we saw that the current, that 4 amps, because these two resistors are in parallel, and they're each 4, they're going to divide that 4 amps into 2 milliamps. each branch here. So using that idea here, we talked about if I put my ground here, I know that node is 4 volts. If I have a current flowing through here, I know that that current has to be what? It's going to be 4 amps here, so I'm going to get 2 times 4, which gives me 8. So therefore, I get a node of 12 volts right there. Since I know that this current is flowing in here and it's not divided, as I said earlier here, then that node relative to the ground, if that's positive and that's negative, then that has to be negative 4 volts. So then the difference between these two gives me 16 volts. So now what happens? Switch is closed. When it's closed, it kills off this whole branch. Here it is. So when I look at this circuit here, I want to determine the Thevenin parameters. Our goal here is to convert it into a Thevenin circuit. So as we do this, what we're seeing here is once again, this circuit has only one current source. So therefore, if this is 4 and this is 4, it's got to divide that by 2. And then you can see that these two guys are in parallel. So if they're in parallel here, then that means that the voltage VOC must be the same as that 2K. So again, because that's 2 milliamps, I get a 4 volt drop, I got my VOC. So as expected, we said what? That the cap was going to discharge. It started at 16 volts and went down to 4 volts. So the jump is 12 volts. So when we calculate the solution for VC, we should see a step of plus 12 in the equation. So then we got to determine RTH. So I open up my source, no dependent sources, so I don't have to calculate high short circuit. And when you look at this, we saw that we have 2 parallel to 4 plus 2. So I get a 6 parallel to 2, which gives me 3 halves. So now I got RTH. And then 1 over tau is 1 over RC. But the way I typically calculate them, I don't typically put them into my calculator unless I absolutely have to. So I just start calculating numbers. So I raise everything to powers. So I know I have a 3 over 2 kilos, so you can see me write 3 over 2 times 10 to the 3. Then the capacitor over here is 100 microfarad. So 100 is 10 to the 2. Micro is 10 to the negative 6. So when I do, that's 5 minus 6 gives me 10 to the negative 1, which is 10. So when I bring that 10 to the negative 1 up here, it's 10. Then I bring the 2 up, so then it gives me 20 over 3 hertz for the time constant. Yes?
When we're determining RTH, we're like using method 1 of the Thevenin.
Because there's no dependent sources. But you're going to see that you'll have some dependent sources in your homework.
Okay.
Then you would be calculating high short circuit. Okay? So now, what I'm left with, I calculated everything, so what do I want to do? I want to go to this. So here I go. So let's look at the voltage of the cap here. So if I look at the voltage of the cap, what we're seeing here is that this VOC is 16. So I'm going to write 16 plus, then I get VOC. Ooh, that's not right. VOC is 4. So then I got to write 4, then VC 0 minus, which is 16 minus 4 times 10 to the minus 20 t over 3. So when I look at this guy, this is going to give me 4 plus 12 e to the minus 20 t over 3 volts. So as expected here, we expected a value of 12. Why? Because there's a step of 12 going from 16 down to 4. So when I draw my, if I was to draw this guy here, you can see that the guy comes in like what? It comes in at 16 volts. And then what it does here is it decays. You can see that as t goes to infinity, this decays down to 4 volts. So if I look at this line right here, this would be my 4 volt line. You'll see that this guy decays from here to there. Now what we're seeing also is that we're also seeing that, what does that number 12 mean? It means that there's a jump or a decay of 12 volts. And so this red curve is given by that guy right there. So that red curve is that equation right there. Okay. So if you were to do this in piece-spice, what would you do? You'd come in and you'd write 16 volts as your initial condition, and then you would see it go from here down to there. If you don't give that initial condition, you won't get that you won't get that graph. Okay, so now what we want to do here is that we now need to solve the circuit problem. So now that I'm armed with this equation for the voltage of the capacitor, I go back to the original circuit. So I would say that this is the original circuit right here, right? We've reduced these resistors right here. We've gotten rid of the voltage source. All I got to do is I got to add the cap back into that circuit. So now I have this guy. And so this is 4K, 2K, 2K, and then I have this guy right here. So I now have my VC. So when I look at the circuit here, if I want to solve for this current, I think I call this current IX, is that correct? Yes. I need to solve for that current IX. One of the things that you can see here is if you're not seeing this, what I would expect you to do here, 12 nodes. 12 nodes. So I need to calculate IX relative to VC here. So we want to calculate IX relative to VC of T. And when you look at that, you can see that I have only 2 nodes between these 2 elements. So therefore, these guys are in parallel. But you can see here the polarity of the current is flowing this way. But when you look at that, you can see that there's a sign difference between the 2. So, if they're in parallel, I have to put in by hand that negative sign. So I'm going to see that the current IX is going to be minus, right, opposite polarity. Then it has to be VC of T divided by its resistor, which is 2K. Just using Ohm's law here. So then if I do that here, I'm going to get that minus sign here. And then, look at that. I'm going to divide everything by 2 now. Okay? I'm going to divide everything by 2. And the currents are now going to be written in milliamps. So I'm going to get 2 into 4 is 2. 2 into 12 is 6. So then I'm going to get minus 2 plus 6 e to the minus 20t over 3 in units of milliamps. And that's the current IX right here. So now, let's plot this and try to interpret this thing here. So when I plot this guy, what do I know here? If I look at this IX here, there is a time before the switch was thrown. So if we go back to the circuit here, we agree that at VC, at 0 minus, we could see that this current across the 2K was 2 milliamps. But relative to this sign here, it's negative. So that means here that this is minus 2 milliamps when T is at 0 minus. After the switch is thrown, it jumps to this guy right here. So when you look at this guy here, it's going to go 2 plus 6 e to the minus 20t over 3 at t equal to 0 plus. So when I look at this here, let's draw the circuit out here. not the circuit, excuse me, the plot. So I'm going to plot this. Plot Ix versus t here. So when I plot this thing here, what am I seeing here? Well, at 0 minus, it's at minus 2 milliamps. So I'm going to come in here and I'm going to say, okay, here's minus 2 milliamps. And then at 0 plus, what I find here is I get this equation. Now let's see if we could just I it. At 0, that exponential here is e to the 0, which is 1. So then I'm going to get minus to minus 6, which gives me minus 8. So then, what happens? This circuit then tells me that there's a discontinuity jump here, right? So if I look at this guy's going to come all the way down here to minus 8 volts. And then you can see here that this guy is then going to do what? Decay back to minus 2 milliamps. So then if I look at this line right here, this guy then does this thing. And what is this equation? Well, this equation is what? Ix equal to minus 2, 6 e to the minus 20 t. So this is plotting Ix of t for all times here. So, does this make physical sense here? Well, what do we really know here? What we really know here is that we know that, so let's try to interpret this. So what we'll see here is that we know that VC of 0 minus and VC at 0 plus must be the same. Is that true? Well, if I look at VC, we said here, we saw that VC here was 16 volts. And then, if I take my equation for the capacitor here, you can see that at t equal to 0, I get 4 plus 12, which is 16 again. So, in each of these scenarios here, we get 16 volts. One of the things that we've talked about a lot in the previous chapter here is that the voltage of cap cannot change instantaneously. But IC of t does change. Right? It can change. As we saw circuits that where it didn't change. But this can change. What I'm saying here is that in general, I'm not putting my 0 minus here. IC of 0 plus is not the same. So let's check this out here. So if I look at IC here, it has to be what? C dV dt. So if I look at my numbers here, what do I have? Well, for C, we saw that C was what? 100 microfarads. So I'm going to put that as a number now. So if I have, let's put it up here. So if I have 100 microfarad, that's 10 to the 2 times 10 to the negative 6, which gives me 10 to the negative 4. So I'm going to write 10 to the negative 4. Now if I take the derivative of my value, I got to take the derivative of this guy here. So then I'm going to get 4 plus 12 e to the minus 20t, 3. And then afterwards, I got to set t equal to 0. I got to take the derivative and then set t equal to 0. So if I look at this guy here, I'm going to get, this guy is a constant. So I'm going to get 10 to the negative 4 times the quantity 0, and then I'm going to get minus 20 times 12 divided by 3 here. So that 3 divided into 12 gives me 4. So I get 4 times 20 gives me 80. So I get 80. And then I'm going to set e to the power of 0, which gives me 1. So what I'm seeing here is that this current here is then going to be what? 80 times 10 to the negative 4, which is the same as what? Minus 80 milliamps for the current of the capacitor at 0 plus. So did the cap change current? Well, let's look at this diagram. So what we're seeing here is that we're seeing IC of t, and we're seeing that at this point right here, right, actually, can I rewrite this just a little bit? I'm going to write this as minus 80 e to the minus 20 t over 3. Okay? So what you're seeing here is that when I calculate this guy, I'm going to get some type of exponential decay. But what is the current of the cap beforehand, when the switch has not been thrown? It has to be 0. Right? It has to be 0. So what you're seeing here is that the current of the cap is coming in at IC of 0 minus, and of course that guy equals 0. And then there's a sudden discontinuity here, where it jumps where? All the way down to here. So it makes a jump all the way down to here, which is minus 80 milliamps. And then what does it do? It just decays back to 0 here. So what we're seeing here, yes?
Negative 80 times 10 to the negative 4 is negative 8. Yeah.
Yes, thank you. I like multiplying by things apparently. So I'm going to take, no, that's 8. Okay, negative 8. So then I'm going to get minus 8 milliamps. So what you're seeing here, even though the voltage of the cap cannot change, the current through the cap is changing, which then forces that current to change instantly as well. And I'm seeing that discontinuity right there. Okay, let's move on. Are there any questions before I move on? Yes.
Does it always work out that the current over the resistor current within is the same? Because the current over that resistor jumps to the
Yeah, and only because these guys were in parallel. So, oh wow, look at this here. Isn't that nice units? Don't let me feed you yes, right? Should be 8 million. I was just trying to see if you were paying attention. So what we want to do now is we want to go towards the inductor. Let me